All right, moving on to section 7.2 notes, where we're going to have your introduction to the concept of functions. The objectives for this lesson is that you should be able to determine if a table, graph, or relation is a function. You should also be able to determine the domain of a function, and also determine the range of a function. So let's start with a couple of vocabulary terminology here. Discrete graph. So first of all, a discrete graph contains discrete data. What discrete data means is that the numbers that we're using to create this graph represent counting values. And what is also true about a discrete graph is that it is a series of graph points that are not connected. So let's now talk about a continuous graph. Continuous graph contains data that is continuous, meaning measurable values. Again, anything where fractions and decimals make sense, then that is data that would be used for a continuous graph. And a continuous graph would be a series of graph points that are connected. All right, so let's look at example number 1 and determine if the situation is discrete or continuous. And we'll see what the graph would look like in either case. So Dan is a car salesman. For each car he sells, he makes $500. Make a table and graph that shows how much Dan makes based on the number of cars he sells, and determine if the data would represent a discrete or continuous situation. So let's first fill in the table. So again, for Dan, he'll make $500 for every car he sells. So if he doesn't sell any cars, then he's earning $0. One car, $500. Two cars, $1,000. Three cars is going to earn Dan $1,500, and 4 cars, since he's making $500 per car, 4 cars is going to earn Dan $2,000. So now let's move on to the graph of this table. So we're going to let the x-axis represent the number of cars, and the y-axis is going to represent the money that Dan can earn. So again, using the table and plotting the points for each scenario, in 0 cars, 0 money. So we got a point at 0, 0, the origin. 1 car, $500. 2 cars, $1,000, and so on. We have our series of points. So now we need to decide if this is discrete or continuous, because that would dictate whether we leave the dots unconnected or we're going to connect them. So now recall that discrete data or discrete graph contains discrete data, which means that the data represents counting numbers or countable values. And in those cases, fractions or decimals do not make sense. Here, because we are talking about the number of cars that Dan can sell, that's our independent variable, right? Since those values cannot be fractional, meaning you cannot sell half a car or 2.5 cars, you can only sell whole cars. That means that this data has to be discrete. Therefore, we are leaving these dots unconnected. All right, so again, this situation is discrete because the data, both the number of cars that can be sold and the amount of money that Dan can earn, cannot be fractional. Move on to example B, where Maria goes to the store to buy grapes. Grapes are sold for $2 per pound. We're going to make a table and a graph that shows how much it would cost for grapes based on the number of pounds purchased. We want to determine if the data would represent a discrete or continuous situation. So again, let's create a table for this situation. So again, we created a table where, again, you buy 0 pounds of grapes, it costs you nothing. 1 pound of grapes is $2. 2 pounds of grapes is $4, and so on. And then, once we completed the table, we moved on to the graph and plotted those ordered pairs. Where again, the independent variable, the pounds of grapes, is along the x-axis, while the dependent variable, the cost of the grapes purchased, is along the y-axis. So now again, we have to decide, should we keep those dots, those points, unconnected, or do we need to connect them? So now, even though our table does not have any decimals or fractions involved, we have to understand that it is possible for Maria to buy the weight of the grapes in a fractional or decimal way. She can buy 1.5 pounds of grapes if she so choose, or 3 3/4 pounds of grapes. Right? It all depends on how many grapes she buys. Okay, so, and that would also make our cost also fractional or in decimals, and depending if the pounds of grapes is in fractions or decimals. So again, because the weight of the grapes is measurable, and where fractions and decimals may occur, even though they're not in our table, this would need to be a continuous situation. Therefore, our graph points need to be connected. Okay, so we connect those points, and we explain again why this is continuous. And this is a continuous situation because it is possible for the data, both the pounds of grapes and the cost, to be fractional or decimal values. All right, so now let's go over some more vocabulary items here. Inputs. The inputs are values that come from the independent variable. Therefore, they are the x values. The inputs are the x values. Outputs. Their values come from the dependent variable. Therefore, the outputs are being represented by the y values of our graph and table. Relation is a set or collection of ordered pairs that come from a table or graph. So again, a relation is a set or collection of ordered pairs that come from a table or graph. Next vocabulary word, domain, is a set of all inputs or x values of a relation. Okay, so a domain is a set of all inputs or x values of a relation, while the range is a set of all outputs or y values of a relation. So again, a range is the set of all outputs or y values of a relation. And finally, function is a relation where every input value leads to exactly one output value. And a function is a relation where every input value leads to exactly one output value. All right, so let's go to exercise 2, where we need to determine if the relations are functions. Then we want to find the domain and the range for each relation. So now remember, a relation is a set of ordered pairs. So every one of these examples is definitely a relation, but not everything is going to be a function. So now remember, what makes a relation a function, is that every input value leads to exactly one output value. So to determine if a relation is a function, we need to look at all of the inputs. Now remember, the inputs are all the x values. So here we highlight all the x values. We got a 0, a 1, a 2, 3, and 4. And since none of those x values repeat, that means every one of these input values leads to exactly one output value. Therefore, this function or this relation is a function. Again, because none of the x values repeat. And this relation is a function, yes, because none of the x values repeat. So now let's list the domain. Remember, the domain is a list or set of all the inputs or x values. When we write that, we're going to write using these set brackets, and we're going to write each of those x values separated by a comma. Now the range values, again, are all the y values. So we're going to take all those y values from those ordered pairs and write them down inside, again, these fancy set brackets separated by commas. Now let's skip over to part D. We want to determine if this relation is indeed a function. So we have to look at the input values. We have to look at the x values. Now right away we see that with the first two ordered pairs that we have a repeating x value. Both these ordered pairs have 1 as an x value. And since those x values repeat, this is not a function. Again, this relation is not a function because we have repeating x values. All right, but we can still answer the remaining questions regarding domain and range. Remember, the domain is a list of all the x values. Now, since some of these x values do repeat, we do not have to write them more than once. Range, again, is a list of all the y values. When you list these, you definitely want to list them from smallest to biggest. Now let's see what you can do with example number 4a. All right, so again, this is a function because none of the input values repeats. The domain, again, is a list of all the input values, while range is a list of all the output values. Now let's move on to the vertical line test. A vertical line test is used to see if a graph is that of a function. When placed at any given x value, if the vertical line intersects the graph only once, then it is a function. All right, so to determine if the graph that we're looking at is that of a function, all you need to do is take a vertical line to your graph. So here I have this red vertical line, so I'm going to go ahead and move it. And you're going to see that wherever I place this vertical line, whether it be here or here, anywhere on this line, on this graph, it only intersects the graph once. And because of that, we know that this graph is that of a function. So this is a function. So now for the domain and range. Domain covers the x-axis. So with respect to this x-axis, this graph goes from -12 to +6. Because there's an open circle right here at -12, we're going to put a parentheses. And because there's a closed circle on 6, we're going to put brackets. The range is about the y values. So you see from this graph, it goes from -8 all the way up to 16. Open circle on -8, parentheses, closed circle on 16, squared off bracket. As you can see here with graph B, that this is not a function, because this vertical line intersects the graph at 2 different points. And this fails the vertical line test. That's it for today's lesson. Go do the homework.